Welcome to this tutorial on computational fluid dynamics. In this video, we will be discussing the fundamentals of CFD starting from the modeling to the simulation and post-processing. We will also cover two commonly methods used in CFD, which are the volume of fluid and the discrete phase model.
Before we dive into the specifics of CFD, let's first discuss what it is and why it's important. CFD is a numerical method used to simulate the behavior of fluids such as air or water in a virtual environment. CFD is used to understand how fluids move, how heat is transferred, and how fluids interact with structures such as planes or ships. The Navier-Stokes equation describes how a fluid, such as air, moves and interacts with its surroundings. It takes into account properties like viscosity, pressure, temperature, and density to describe how the fluid behaves. This equation is particularly relevant to aerodynamics in aerospace because it can be used to predict the behavior of air around the object in motion, such as an airplane or spacecraft. By understanding how the air flows around the object, engineers can design more efficient and safer vehicles. However, solving the Navier-Stokes equation for complex problems is extremely difficult and requires the use of advanced numerical techniques and high-performance computing. As a result, computational fluid dynamics has become a powerful tool for simulating fluid flow around the space vehicles and optimizing their design. CFD is important because it enables engineers and scientists to design and optimize products without the need for expensive and time-consuming physical experiments. CFD can be used to study complex fluid dynamics problems that would be impossible to study experimentally.
The basic principles of computational fluid dynamics include the conservation of loss. CFD is based on the principles of conservation of mass, momentum, and energy. These laws state that the amount of these quantities in a system is covered over time and any changes must be accounted for. Continuum assumption. CFD assumes that a fluid can be treated as a continuous medium rather than a collection of individual particles. This means that the properties of fluid such as density, pressure, and temperature are assumed to be continuous functions of space and time. Mathematical modeling. CFD uses mathematical models to describe the behavior of fluids. These models are derived from the conservation laws and other physical principles and are expressed as sets of partial differential equations. Numerical methods. CFD uses numerical methods to solve the partial differential equations that describe the behavior of fluids. These methods involve dividing the fluid domain into a grid of discrete cells and applying numerical algorithms to calculate the values of fluid properties at each point in the grid. Validation and verification. CFD results must be validated and verified to ensure their accuracy and reliability. This involves comparing simulation results to experimental data and other validated simulations. These principles are used to simulate the behavior of fluids in a wide range of applications, from designing aircraft and spacecraft to modeling weather patterns and predicting the spread of pollution.
The first step in any CFD simulation is to create a model of the physical problem that you want to simulate. This model can be created using CAD software or by drawing the geometry in a software like Ansys. It's important to ensure that the model accurately represents the physical problem and includes all the necessary features such as inlets, outlets, and boundaries. For this example, and in our experience, we commonly use SolidWorks to create the 2D and 3D models to be simulated, then simply save it as the default SolidWorks file type. When creating a model, you'll want to make sure that it's a closed solid. This means that there are no gaps or holes in the model that would allow fluid to escape. You'll also want to make sure that the model has the right level of detail, meaning it's fine enough to capture all the important features of the flow, but not so fine that it'll take an unreasonable amount of time to compute.
So for this example, we would be using the 3D model of a coaxial swirl injector. So as mentioned by the previous presenter, in modeling for a computational fluid dynamics simulation, you have to make sure that the inlets and the outlets of your model are clearly defined. And then aside from that, the model must be closed, wherein it covers the entire domain of what you want to simulate. So for this example, our inlets would be our pipes in here, which would be for our oxidizer, our fuel, that will be injected into the system. And then our outlet for this problem would be on the side and bottom of the largest cylinder, which would represent the outer atmosphere that the spray would be diffusing to. And then everything else would be the model of the walls.
The next step is create a mesh, which is a collection of small cells or elements that make up the physical domain. This is done using meshing software such as Ansys meshing. The mesh should be fine enough to capture all the important features of the flow, while also being coarse enough to ensure reasonable computational times. In simulating, the computer basically solves the different equations for the many variables in a finite space, which is called a single cell. A collection of these cells in your simulation is simply the mesh. When creating a mesh, you want to ensure that the cells are well distributed, meaning they aren't too clustered or too sparse in any particular area of the model. You'll also want to ensure that the cells are the right size, meaning they're small enough to capture the important flow features, but not so small that it'll take an unreasonable amount of time to compute.
So in order to start off with Ansys Fluent, after you have modeled the domain for your simulation, you simply start up Ansys Workbench with whatever version you have. And from there, you will be greeted with this screen as can be seen below. Now, these two components would not be here normally, but they are here for the sake of demonstration. So how would you add your own fluid simulation? You start off with the analysis systems located on the left. From here, you would drag Fluid Flow Fluent or any other component system that you would like to include towards the center. And from there, these are the certain steps that you have to take in order to create your own simulation. So for geometry, we have already completed the model in another application, SolidWorks. So now we just right-click on our geometry, click Import, and then Browse. And then from there, we would just select the geometry that we would be using. And as you can see, a check mark appears and the mesh icon turns a different color. And from there, we can double-click the mesh. Now that the meshing screen has opened in Ansys Fluent, this is what you will see. Now from here, we have not yet created a mesh. As you can see here on the left side of the tree, the mesh icon has a lightning icon next to it. That means the mesh needs to be updated or generated. We can do that by clicking on the generate above. And now it will take some time to load depending on the speed of your system. And now it will load the default mesh for our model. As you can see here, and we zoom in, this is the default mesh that it has created. Now, in Ansys Fluent, there are cases where the default mesh is not fine enough, where it needs to be smaller. The single elements need to be smaller in order to have a more accurate solution. Now, how would we do this? There are multiple ways to do this, but the most common and basic way to do it would be to go over to the mesh, click mesh, and below you can see the element size option. And you can change that to whatever value you see fit that will create a finer mesh. And we can see that later once it turns pink and we click generate. And now we can visibly see that the mesh is now finer, more elements are present, and the individual meshes in the model are now smaller. So what does this mean? This means that the mesh can now produce a solution that is more accurate, but it would also take more time. Now, in certain flows, it is more advantageous to employ other techniques such as the method, the sizing, contact sizing, phase meshing, and other forms of mesh refinement, including inflation. But for this model, all areas of the flow are important, and thus they need to be more or less in the same size. But this is applicable for only very few cases, such as these ones. Now that we have employed other techniques or whatever techniques that we have found fitting in order to create a finer and more appropriate mesh for our solution and our problem, now we have to set our boundary conditions. As mentioned earlier in the modeling portion, that the inlets and outlets have to be clearly defined in our model, and the entire model has to be sealed or watertight. And now, how do we go about and name our oxidizer and fuel inlets? So to do that, you would click the space option here, or whichever option in the selections is applicable, and click on the faces that we want to rename. So in Ansys Fluent, when we rename something into an outlet or an inlet or even walls, the program automatically assigns them the appropriate type. So if you go here and then right click and we name this oxidizer dash inlet, when we open the Ansys Fluent proper later in the solution portion, this space will then be automatically assigned as the inlet of our problem. And then we would go about and do the same for our other fuel inlets. And for our outlets, the keywords that the program will automatically associate is the outlet. And then for everything else, we would just deselect the ones that we have selected here. We would right click create name selection, and then we would name it walls in order for an automatic reassignment of its appropriate type. So here, we could just make further changes to the mesh, or once we have no more changes to make, we would just close this window and then go ahead and save. And then, before proceeding to the setup portion of Ansys Fluent, we would right-click the Mesh tab and then click Update. And now it will take some time to update and run over the mesh again. But once this is finished updating, the icons will change and we can move on to the setup portion of our computational fluid dynamics simulation.
Once the mesh is created, we can now specify the boundary conditions for the simulation. Boundary conditions define the behavior of the fluid at the boundaries of the physical domain. These include the velocity of the fluid at the inlet and the pressure at the outlet. It also involves specifying the fluid properties such as its density and its viscosity. When setting up boundary conditions, it's important to ensure that you've specified the right conditions for the physical problem you're simulating. You'll also want to ensure that the boundary conditions are consistent with each other and with the physical problem.
Now that we've created the model, mesh, and specified the boundary conditions, we can now solve the equations that govern fluid flow. These are different solvers available, such as Ansys Fluent, which can solve the equation using numerical methods such as the finite volume method. When solving the equations, it's important to ensure that the simulation is properly set up and that the solver parameters are selected correctly. You'll also want to ensure that the simulation is run long enough to reach a steady state or obtain the desired transient behavior.
So now that the meshing update has finished and we have saved our project, we would go now and double click on the setup portion. So here, we would just wait for the Fluent launcher to load. And for these options, we would like to always tick double precision. And now for the solver processes, this would be the number of processes that the CPU will use. Now for a general rule of thumb, since hyper-threading is on for most CPUs in the current line that is being released in the market, we would usually just saturate our CPU. So you would go for your number of cores times 2. So my machine has 16 cores, but for hyper-threading, it will only give a total of 20 virtual cores. So that means our solver processes would be at 20. And from there, we could just click Start. And now we wait as the main Fluent window opens and loads our previous data that we have inputted, such as our mesh, our boundary conditions, and load in the plugins that we need.
The volume of fluid method is a commonly used technique in CFD to simulate free surface flows such as waves or sloshing liquids. The volume of fluid method tracks the position of the fluid interface by assigning a volume fraction to each cell in the mesh. The volume fraction represents the fraction of the cell that is occupied by the fluid. This method can be implemented in Ansys Fluent by selecting the VOF model under the Multi-Phase Models tab. When using the VOF method, it's important to ensure that the mesh is fine enough to capture the important fluid interface dynamics.
So now I have loaded up a case wherein all the settings are put in so that there is a more smooth flow of explaining the different options that we have in Ansys Fluent. So now we have just gone into the multi-phase model option and turned on the volume of fluid. Now I haven't changed any options here and have kept it basically towards the default settings. The only one changed here is the number of Eulerian phases, which basically means the number of different materials that we will have interacting with each other. Now we have place 2, one for air and the other phase for water liquid. So now we have gone to the phases tab, and here we can see the different phase setups. So now we will simply give a name for each phase and assign a material. So one for air, one for water. Now moving on to the phase interaction in the forces. Here we will specify the different forces that are at play between the two phases, specifically the surface tension coefficient. So this is a standard between air and water at a constant 0.072 Newton per meter. And we have also turned on the different global options here, and the more you turn on, the more complex and more accurate the simulation will be. So now we can just close that because we have no options for heat mass reactions. The next option that we would be turning on would be the discrete phase models. So now for discrete phase models, this will be explained in another portion of the video. But for this, we will have the interaction with a continuous phase wherein the individual particles that we have simulated will interact with our continuous phase, which in this case is air. And we will update our DPM sources every flow iteration. So now, for the physical models, we have simply selected the pressure gradient force, the two-way turbulence coupling, and for this example, we will also turn on the scholastic collision for coalescence and breakup.
The discrete phase model or DPM method is another commonly method used in CFD to simulate the behavior of particles or droplets within a fluid. The DPM methods tracks the position, velocity, and other properties of individual particles as they move through the fluid domain. The DPM method can also be used to simulate phenomena such as spray combustion, particle deposition, and inhalation of particles. The DPM method can be implemented in Ansys Fluent by selecting the DPM model under the Multi-Phase Models tab. When using the DPM method, it's important to ensure that you've selected the right model parameters. For example, you'll want to specify the size, density, and velocity of the particles, as well as any relevant fluid-particle interaction parameters. You also want to ensure that the mesh is fine enough to capture the important particle motion.
So now our injection tab has opened, and we are now creating an injection from which we will inject our particles for the DPM simulation. So now we have selected our injection types, set the appropriate values here for the position and velocity. Now that would depend on the model. And we have selected our material of water liquid DPM. DPM standing for discrete phase model, as it is an inert particle that will stay constant aside from the breakup and coalescence equations to be used. So after that, we are basically finished with the models page, and we will be moving on to the materials, wherein we have specified air, water liquid, and water liquid DPM. So that would already be specified in the models tab as explained earlier. So now for our boundary conditions, we have already set our fuel inlet, outlet, oxidizer inlet, and our walls automatically from the start. But for our fuel inlet, we would go edit as a pressure inlet, and we would set the gauge pressure as set by the problem given, which in this case is 10.8 megapascal. Same with our oxidizer inlet as a pressure inlet, 10.8 megapascals. So now, we will be moving on to our methods. Now the methods page is basically the different methods that will be used in order to solve for the different aspects of our simulation. So here, we have our pressure, our momentum, our volume fraction, and our turbulent kinetic energy, and etc. Now for this, we would be using the defaults provided. Next up, before the simulation, is the initialization of our simulation. So initialization means solving the very first equation at the very start, or the very initial conditions that we have set. So these are the initial values at the very start of the simulation. And now we would just click standard initialization and then initialize. For this, hybrid initialization would also work, as these two are interchangeable in most cases. So now we would go over to calculation activities after our initialization, and then autosave every 100 iterations, or how often we want to save the data that we have created. So that could be depending on the time step or on every iteration of our simulation. And from there, we would go to our run calculation and then set the number of iterations that we want for steady simulations, or the number of time steps that we want for transient simulations. And then the time scale factor for steady simulations basically means that how slow would we want the simulation to go for a pseudo time step method. And then you would just simply click on the calculate, and the mesh will be solved.
Once the simulation is complete, we can now analyze and visualize the results using post-processing. This involves extracting important data such as velocity and pressure distributions, and visualizing the results using softwares like Ansys CFD Post. When post-processing, it's important to ensure that you've selected the right visualization options and that you've extracted all the important data. You'll also want to ensure that you've validated your results by comparing them to experimental data or other simulation results.
So now that the simulation has finished, it will pop up calculation complete, and then we would close the Ansys Fluent application. And we would be back to this screen. Now, we would double click the results tab, and that will start up CFD Post, which is the default post-processing option of Ansys Fluent. And now we would wait for our results and our model to load in. So now, this is our screen. So first, it will load in any data that it has, but in order to display that data, you would have to make our own ways to visualize that data. So the very basic ones would be our contour, our volume rendering, and our ISO surfaces. So for now, we would like to visualize the ISO surface of the water, or what would the water look like in our model. So we'd simply go here to ISO surface. Now ISO surface is basically a plane that would follow the different data that we have gathered from our simulation based on what we want to display. So for now, we would display the volume fraction of our water phase at a value of 0.1 in the lower left, and then we would click apply. And that will load in. And the water with a volume fraction of 0.1 will be displayed as a single surface. Now we can play around with that value and show even more. And these are just some examples. So here we can visualize the air core formation of the coaxial swirl injector. And now, aside from our ISO surfaces, we can also create our own plane. So in order to create our own planes, we would go here to location and then click on plane. And we would want it to be on the XY plane depending on these points here in the coordinates. We click apply. So if you go to the front view, we can see that the plane is just flat up close. So now we'll just hide the plane, but the plane is still there, and then create a contour with this icon here. So basically, a contour is kind of like a heat map wherein higher points are set to a different color compared to the lower points. And now, what we would want to see is the velocity. So from here, we would find the variable for velocity, the range global, and for the number of contours, the maximum would be 255. And then we will click apply. But don't forget for the locations to be set, as the contour is only a surface. So as you can see here, when we clicked apply, it only appeared on the fuel inlet sides as it is set here. So you would select the location as the plane that we have created earlier, and then we will click apply here, and then velocity apply. So now the data will be loaded in, and as we can see, the velocity contour is now showing. So we can see here that our maximum velocity is at 140.9 meters per second, and our slowest is at 0 meters per second. And now we can also quickly switch this over to other variables such as our pressure. And we can also do it for our volume fraction of the water. We can also change how we want the data to be showed, such as the color. We would just go here to the number of contours, click advanced properties, and then color map. Here we can find different presets on different variables that we can show, such as here in the field liquid, field phase fraction. So this field phase fraction is basically a preset for volume fraction rendering. So we'll just click apply here to see what that would look like. And as you can see here, it has changed the colors depending on the preset. So we would just go and hide our contour, and then we would go here to our volume rendering. So basically from a 2D rendering of our contour, it would become a 3D rendering through a volume. So domains would be all domains, range global, and our variable will be our volume fraction. Resolution, same as earlier, 255 for the maximum, and then click apply. And then from here, it would calculate the volume rendering, and this is the part that kind of takes a while as it takes into account the 3D data of our model. And now if we move around, we can see here that it has created sort of a hazy volume rendering of our data. So now we have loaded up a case wherein this is a transient simulation of a discrete phase model for the same coaxial swirl injector. We have loaded this up in order to properly explain discrete phase model, as this one is a better example. So now that the simulation has finished, this is the result of the simulation. So now, in order to create the post-processing elements of our DPM, we can go ahead and create an animation. And we can do that by right-clicking on our playback animations in the left side of our tree, click edit, and then we would click read, and then find the DPM data of our simulation. So you would just go to the folder where the simulation was done, and here we can find this option. And now we will click our animation sequences, write record format as a video file, change the different video options that we need, such as the FPS and the resolution. And then once we are ready, we can click write. And then that will write the video towards our working folder of where we saved the project. So we would just go ahead and close that up, and then just go and find the results. So once the simulation has finished running the animation, we can find here the different animation files that we have created. And if we would just play that, it would show the animation of the simulation as can be seen here. So each and every individual particle is simulated. So this is the purpose of the discrete phase model, in order to find the different interactions of the different particles with each other. This is another animation that we have created earlier. So aside from these animations and in the simulation, we can also find the different scientific data that we can get. So under here in reports for discrete phase, we would just click our summary and then edit. And then we would click for either injections, both or just one injection, which we would like to find the summary. And click close. And if we open up our console, it will show here the different summary for our injections. So you can see here the total number of parcels or particles injected, what was the overall mass that we have injected into the system, and their overall volume diameter, solder diameter, its minimum and maximum particle diameters. So then here would come the post-processing parts of our data. So for this example, the most important data here would be the minimum and maximum particle diameters, as well as the solder mean diameter. And that would be it for the post-processing of both volume of fluid and discrete phase model portions of the simulation. Got it.
In conclusion, CFD is a powerful tool for simulating the behavior of fluids and understanding complex fluid dynamic problems. By following the steps we've outlined in this tutorial, you can create accurate and reliable simulations of fluid flow. We hope you found this tutorial helpful in understanding the fundamentals of CFD. Thank you so much for watching! This is Norbeth Mejia.
This is Brendan Calabazaron.
And this is George Mercurio, demonstrating the different simulations used in the thesis titled Design and Characterization of a Coaxial Swirl Injector through Computational Fluid Dynamics.